Thank you very much for the invitation to be here. It's been a very, very nice conference, and thank you everyone for coming. So this might be a slightly eccentric talk. So I'm a Riemannian geometer, but somehow, well, this is beyond finite dimensions, so that's more infinite dimensions, and there are some infinite dimensional spaces here, and there is curvature, but actually this is some sort of like sideways look into some problems that come from data analysis. So, but first, what's the plan? This is more, well, I will discuss like Alexandrov spaces. This is part metric geometry, then some motivation and examples from data analysis, actually like topological data analysis, and then how, well, these persistence diagrams are objects coming from data analysis, and basically one wants to do statistics on these sets of objects, and then try to say something about the data, and then this is where sort of these two things merge. And so this is, well, okay, so what is the theme of the talk is, well, you have some space, right? And does it actually support a nice geometry? I mean, nice in the sense that, well, it lets you do what you want to do. So maybe you want to, in this case, one of the main goals is to try to compute, say, barycenters or averages, or maybe, as I say, do statistics. So one is free to choose, what does this mean? So here, the spaces or the sets come from topological data analysis, and then want to connect them with geometry. And here, this is the spaces of persistence diagrams, and here, Alexandrov spaces. So probably everyone is familiar with Alexandrov spaces, but let me just remind you. So we start with this. So what is the motivation for Alexandrov geometry? Is Riemannian geometry, right? Sectional curvature. So we have a Riemannian manifold, and the Riemannian manifold has curvatures. Here, curvature will be sectional curvature. So this is, right, you can detect it by a triangle comparison. And the idea is to take some spaces that look like Riemannian manifolds. So these are length spaces. They have already shown up. I just remind you after lunch, right? What is the distance, right? So we look at distances that are intrinsic or length metrics, right? So this is how the Riemannian distance is constructed. You take, say, 2 points, and then you compute the length of this curve. So you take a partition, and then you start looking at the distance between consecutive points. This is just the curve in R2. So this is the distance. This is the length of these straight lines, and then you take finer and finer partitions, and then you take the supremum, right? And if that is finite, you say the curve is rectifiable, and then this distance is the infimum of the length of rectifiable curves joining 2 points. So that is those are length spaces. So again, Riemannian manifolds are the archetypical examples of these spaces. And then we want to do triangle comparisons. So we have to look at geodesic triangles. So here a geodesic will be a shortest curve. That's just the curve realizing the distance between its endpoints. And a length space is geodesic if any 2 points can be joined by a geodesic. For example, complete Riemannian manifolds are geodesic. And so now we want to compare curvature. And so the idea, right, as you might already know, is compare triangles in the space with model spaces. Like this also appeared in Clement's talk yesterday. So here we take the model spaces are Riemannian. So we have the round two sphere, the flat, the Euclidean space, and here hyperbolic space. And well, in a length space, we only know distances. Okay, so we want to compare triangles. So a triangle in a geodesic space is just 3 points. And then we look at a comparison triangle. It's 3 points in the comparison space, whose sides have the same length as the sides of the comparison triangle. And then we have this property that comes from Toponogov's theorem in Riemannian geometry. So we have 3 points in our geodesic space, and then we have a comparison triangle, and then we say that this property holds that if so we have the lengths of these triangles are the same, and this property holds if for any point S on this side, we have here, well, you fix a point here, and then this side has the same length as this side. You fix, so there's a corresponding comparison point, and then you look at the distance from P to S, and we want that to be greater than or equal this length. So that's just the definition. So this is, you can think of this as a metric manifestation of having a lower sectional curvature bound. So this is Toponogov's theorem. So then you take this as a definition for geodesic spaces. So this is, so now we just have this lower sectional curvature bound, and then an Alexandrov space with curvature bounded below by K is a complete geodesic space where this property holds locally. So for example, this is an Alexandrov space. This tetrahedron is homomorphic to a sphere, but metrically, right? It's not smooth. It's flat right here, and here you can do triangle comparison, and that has. So you can think of those points as having sectional curvature greater than or equal 0. But these, for example, trees are not Alexandrov spaces. So here, for example, if you want to do triangle comparison, a triangle would look like a T, right? And you cannot, you don't have a lower curvature bound. So these have an upper curvature bound, but for the purpose of this talk, we're going to look at lower curvature bound. So, okay, so what are properties? So geodesics do not branch. This was also briefly mentioned yesterday by Clemens. When has the property, this triangle comparison holds for triangles globally. And right, and then the Hausdorff dimension is an integer or infinity. So in that sense, so Alexandrov spaces look like Riemannian manifolds, right? So they're topologically they're regular in the sense that you do not have some sort of like fractals or things that might not be sort of that are maybe unsuitable for topological questions. So actually, in Riemannian geometry, sectional curvature is very much related to topology. So here, so Alexandrov spaces you can actually answer topological questions. So what are examples, right? So complete Riemannian manifolds with a lower sectional curvature bound, so convex boundaries of convex bodies in Rm. These have non-negative curvature. You can take cones and suspensions of spaces with curvature bounded below by 1. So these are like the generalizations of the round sphere. So for example, here you can take a, for example, complex projective space. That's a manifold that has a metric with curvature greater, sectional curvature greater than or equal to 1. You can take its suspension. That's no longer a manifold, right? So, but its topology is relatively simple, right? It just has 2 singular points. So one can also glue spaces. So this is a theorem due to Perelman originally for doubles, and then by Petrunin for general spaces that have isometric boundaries. Now, this is also where they arise in Riemannian geometry fairly often as quotients of Riemannian manifolds by groups of isometries. So here, this is more generally, if this is an Alexandrov space with curvature bounded below by K, and G is acting by isometries, then the quotient is going to be, again, an Alexandrov space with the same lower curvature bound. And originally, or historically, they arose also in this way. You can look at pre-compact classes of Riemannian manifolds, right? And then you take the closure under the Gromov-Hausdorff distance, and these are Alexandrov spaces. So for example, here you take the sequence of Riemannian manifolds with a uniform lower sectional curvature bound and uniform dimension, and then the limit is an Alexandrov space. Now here, the limit might collapse, right? You can have, so this is, in this way, they're very useful in questions in Riemannian geometry. But of course, one can also just study them on their own. And well, in infinite dimensions, one has also Hilbert spaces and Wasserstein spaces also in some instances. So, okay, so now for topology. So what is their local structure? So, I mean, you can think of the main intuition, you can think of a Riemannian manifold, right? So in a Riemannian manifold, you have a point, then you have the tangent space, and then you have a unit tangent sphere, right? So so in the unit tangent sphere, you have angles, right? It's you have unit vectors and then the angle. And then here, one can generalize the notion of angles between geodesics. And then you get tangential directions, and then you take you can construct a metric space called the space of directions. That is the generalization of a unit round tangent sphere. So, but this might no longer, this is not necessarily a sphere. So there's this fundamental theorem of Burago-Gromov-Van-Perelman that if the space has finite dimension, then this is an Alexander space of curvature bounded below by 1. Think, for example, in the Riemannian case, this is a round unit sphere. It has constant sectional curvature 1. And it has dimension 1 less than that of the space. And then in in Riemannian geometry, you have the exponential map, and one learns that if you take a point, right, then a sufficiently small neighborhood of that point is diffeomorphic to a ball in the tangent space. So this is so basically what this is saying is that the local well, among many things, is that the local structure of the Riemannian manifold is controlled by the tangential structure. So here there's an analog, an extension of that due to Perelman. So this is a very deep result that every point has a neighborhood that's pointed homeomorphic to the cone over the space of directions. So what this is saying is that the local topology is controlled by spaces that have positive curvature. So maybe you've seen why Riemannian geometers are very much invested in understanding spaces with positive curvature. So this is also one. I mean, they control the geometry of these of Alexandrov spaces. And this also says, well, if you want to understand the local geometry, you need to understand these spaces. So actually, beyond dimension 3, right, Riemannian manifolds with positive curvature are not classified beyond dimension 3. So, but in low dimensions, one can, these are classified also in the Alexandrov case. And so what is known about low dimensional spaces, right? So in dimensions 1 and 2, these are homeomorphic to manifolds, possibly with boundary. And then, therefore, one knows all the spaces of directions in dimensions 1 and 2 and 3. So for example, in dimension 3, the space of directions is 2-dimensional. It's positively curved, and there's an extension of the Myers theorem. So one can show that a positively curved Alexandrov space is compact, so it has finite fundamental group. So what this is saying is that the positively curved Alexandrov spaces in dimension 2 are S2 and RP2. So what that means is that locally a space in dimension 3 looks like a cone over S2, so therefore it's a manifold point, or it's a cone over RP2. And then, well, one can, this is some work I did 10 years ago, with Luis Guijarro. And then in dimension 3, one understands basically how these spaces are constructed. So they're either topological manifolds, or if it's not a manifold, it's the quotient of a topological manifold by an involution that reverses the orientation. And then one can use that to classify three-dimensional Alexander spaces with positive curvature. So actually, they're all spherical manifolds, or it's a suspension of RP2. So they're not that many. And this also gives you the local structure in dimension 4. But beyond that, well, they can be, you can have orbifolds, you can have complicated spaces. And well, you might think, okay, this is very similar to Riemannian geometry. In a way it is, but you have to keep in mind that here there's no smoothness, there's no, one has to just use the metric. I mean, but somehow here, one has to link all this curvature with the global topology of the space. Okay, so this is, I mean, in terms of topology, this is, well, one has fairly complete information about how these spaces look, or how they arise. But now, right, what's happening in infinite dimensions, right? So most of the spaces or the theorems that I wrote, for example, Perelman's neighborhood theorem, are for finite dimensions. So actually, in infinite dimensions, well, this is a natural question, of course. What are the corresponding results? And actually, there's not much is known. So actually, well, there's some work by Mitsuishi and Yokota and Conrad Plaut, but there are very few results known. So actually, there are some also, there might be some strange phenomena, right? Like the spaces of directions might not be compact. So things are different, certainly. So here, this is maybe one question that deserves attention, I think. And then, well, the next part of the talk is about some spaces that are infinite dimensional and arise from topological data analysis. So this was, and this might be sort of maybe good for generating some intuition, and they're also might be useful in other contexts. So, okay, so now on to the next part of the talk. So we're going to leave geometry a little bit and go to sort of move sideways to this data world. And maybe you've heard of topological data analysis. So the idea is to, if you have a lot, like a point cloud of data, and you want to sort of get some topological invariants that give you some information about the shape of the data. So I'm not going to define things rigorously. Rather, I want you to sort of get the idea of what are the questions, or what is the idea behind this. So the general framework is that, well, you have some data sets, some points in a metric space. Just think of R2 here. And then one builds some simplicial complex that's filtered. You can think it's parametrized by sort of 0 infinity. And then out of that, you compute something called a persistent homology of the complex. And then you get something called a persistence diagram. So I will tell you more how this is done. So this persistence diagram consists of points in this upper octant, and correspond to some sort of generators of 0 and 1-dimensional topology. Homology that you can build out of this complex. So you can, I mean, one of the intuitions of this is sort of how many holes or sort of loops the data set has at different scales. Okay, so so this is more, again, this is how one the steps. So you have some data set, you have this filtration, that here it's parameterized by R. Then you get something called a persistent module, that is, again, it's parameterized by R, and these are homology groups, and then you look at the generators. So these are sort of the persistent, these represent when these generators sort of appear, and then when they disappear. So, okay, so let's make that more concrete. So we have this data set, and so here is the sort of, imagine here, I mean, the idea is, what is the idea? Maybe in practice, right, you do not know the sort of the underlying space of the data. So maybe you want to say, well, is this data sort of does it look like a circle? Say. So here, of course, we can say yes. But imagine here you sample, you take points from a circle, but there is some noise. Okay, and then how one constructs, one way of constructing this simplicial complex is as follows. So you take circles or disks, and then you start sort of growing the radius. So that went pretty fast. So I think this is with the Adobe, but okay, that's fine. So here you can imagine these circles are already pretty big. And then when these circles, these disks intersect, you join the centers by an edge. Okay, and then you compute the simplicial homology at that time. And then, right, for example, here we have this, this looks like, well, this has, this already, say, homotopy equivalent to a circle. So you have, you keep sort of, you will have one generator of homology, and then you just keep making the circles bigger and bigger until then eventually they overlap, and you have a ball, and then you say, well, this sort of generator dies. So for the, yes? Right, so maybe, no, of simplices, yes, right. So maybe, yeah, fortunately I have this other picture that might, thanks, no, good. Yeah, actually this was supposed to last like maybe 5 seconds or something, but it's sort of like a little movie. But yes, good, thanks for asking that. So, right, so here this is a little like a sort of step by step. So you have these points, this is another point set, then you start growing this. So for example, these, they grow, these are sort of overlapping. So here, for example, you would sort of join them by an edge. And then here, these are all overlapping. So you have this. So this is the, you compute the homology of this one. So here, these represent generators of the zeroth homology, which are connected components. Here, you sort of grow. And then here, for example, now you have first homology, right? You have these loops. So this means that at some time t, there's this sort of is born, you have this loop, and then it lasts, and then you have this other one, which will correspond to this one. And then, for example, here you keep growing. I mean, in practice here, you would fill by two simplex, by a ball. And then this generator of the first dimensional homology just dies, right? So this would be this, but this one is still going, so you keep growing, but eventually everything overlaps and then everything just dies, and you're left with one connected component, okay? So this, in practice, so you have, this is born, say, at time t1, and then dies at time t2. So what you have in the end, this is called a barcode. It's a collection of intervals, and they correspond, and these are the points in this octant, and this is the persistence diagram. This is sort of intuitively what is happening. And then these are the well, these objects somehow, well, in some sense, contain information about the data. Now, this can be done, you can compute it for, right, kth homology, but actually maybe if you see some applications, in practice, this is computationally quite expensive, and then usually one, yes, I think. Yeah. Yeah. You basically, right, so yes, so basically what you do is, so if a generator is born at time t1, right, and then this is t2, then these are the coordinates of these points. That's basically it. Yes, right. So right, so these, for example, they're born pretty early and then it dies pretty early. So these are, and then for example, this one, corresponds to this. So that's right. And for example, points that are very close to the diagonal, these are points that sort of, or generators that appear, but then disappear very quickly. So you can think of them as being sort of noise, right? So these ones are more sort of, yes.
How do you identify which?
Yeah, right. They're not ordered. Yes, right. Here, yes. No, this is right. No, yes. Sure.
Also change
No, because they have just the same. These are basically the lengths of these bars are the coordinates of the, not the lengths, but the time where it dies, the time where it's born, and the time where it dies. Those are the coordinates of this point. Well, in what you mean if they appear and die at the same time?
No. You know which one.
You mean how do you keep track of that, or? Well, I guess in practice you just you compute this in real. I mean, does that answer your question or not really?
Just from knowing the.
No, right? Yes. I mean, what you do. Well, okay. I agree. Yeah. I mean, I'm sweeping a lot of things under the rug. Yes. I mean, there's like a whole. Right. I mean, there's more. There's more that you can keep track of that. Yes. But yes. Yeah. Here, I chose not to go into those details because what I wanted to get is here, and these are the things that I mean. But yes, you can do it. Yes. So, is that a satisfactory answer? Yes. Okay. Yeah. Okay. So, all right. So, okay. So these are the things. So this is sort of in theory, and okay. So now an example to see that it's actually or you can see it in action. So this is actually this is a volcano in Mexico, right? It's actually this photo won some prize, so I thought I bet you were not expecting to see such thing in the talk. So, but now, okay. So again, this went really quickly, but fortunately, I have them. Yeah, what is happening here? So I have a copy of step by step. So this is something that actually this is done in practice. So these are actually sort of signals from a seismograph in the volcano, and there is a way of sort of generating a point cloud from this signal. Right? There's actually also some mathematics there. There's something called the Takens embedding theorem that's from dynamical systems, and so people have used it to generate some point cloud, and then you can do this procedure, compute this persistence homology. So you get this point cloud, and so I'll just say this is some event, something is happening. So well, this is not the scale changes, but here, for example, you can see there's like a lot going on. Then this is happening, so there's some magnitude that sort of means somehow is related to the sort of strength of this event. And here there's a lot more going on. Things get complicated, and then it goes back to things die down. And then here you can see in reality, if things were to scale, all these points are very close to the diagonal. So this is sort of like noise. So right. Okay, so now what is this? So, okay, so if you have this, one would like to say generate some information out of this. So what does this thing look on average? Okay, so this is the problem I was mentioning at the beginning, that one would like to have some notion of actually having like a barycenter, right? How to compute averages for this. And so this is one way of doing this. So actually, from here to here, from these you generate the point cloud. You do this, and then from here to here, you represent this by, this is also a picture, but what this is a sequence of functions. So from here to here, you map these objects to functions so these are in the Banach space, and then there you compute an average. So this, now the issue here is that So, okay, so these are called persistence landscapes, and this is something called the average landscape. But okay, each one of these corresponds to some function that somehow represents the average. But you can see that these graphs do not look like these ones, right? These are piecewise linear, but what this means is that this object, this function, is not coming from a persistence diagram. So this is something that this is an average that leaves the space of persistence diagrams. So okay, I mean, this is fine. I think in practice, people need to compute things, so this is sort of has some advantages, but from a more theoretical point of view, one would like to say you want to do things intrinsically, right? So this is where things enter. So we want to look. Yeah, yes. Sorry. These ones. What is the data here? Okay, yeah, the data here is a signal. It's like here you basically have this is the seismogram, yeah. And then you take just a piece of the seismogram, and then what you have is a time series, they call it. And then from this time series, you can generate a point cloud, basically. So from here to here, there is some black box that is, you generate a point cloud. Maybe I should, yeah, that's a good question. Next time I'll add that picture there. So yeah, and then from that point cloud, you generate this. And from this, you represent this as these objects for which you can take an average. But the average leaves the space, right? The average is no longer a persistent, you cannot map it back to a persistent diagram. So, right, so yeah, so then, well, this motivates this, how can one geometrize this space of persistence diagrams, or actually model them? So now we go back to more like mathematics, yeah. So, right, so now what is a persistence diagram, right? So this is a multi-set, so you can repeat points, and each element is a countable collection of points right here. Basically, they lie in this, above the upper diagonal in this octant, and then you add countably infinitely many copies of the diagonal. Okay, so why do we want to do that? So basically, this is so that we can compute a distance. So for any p, you can define the p-Wasserstein distance between diagrams as follows, right? Basically, you have bijections between the elements, so they're countable. So so then you can compute the distance. That's why you add this. If you have finitely many points and then the number is different, you cannot match them. So you add this diagonal so that you can compute this. Okay, so this is the distance that we look at. So this was done by Milei, Kumikirti, and Harer some time ago. And so the motivation, again, was to try to compute things intrinsically. So here, these are the matchings, right? So if you have 2 points, you match them here, but there are maybe points that are not matched, and you match them, but you compute the distance to the diagonal. So, okay, right. So this one has a distinguished point. There's the diagram that consists of only copies of the diagonal, and now you look at all the points that had a finite distance. Okay, so this is like the analog of the Wasserstein space, and then so this is so what I can see, and you prove it by hand, that this is a complete and separable metric space for any p, and then for p equals 2, this is actually an Alexander space of non-negative curvature. It's infinite dimensional. So actually, yeah, I mean, this paper seemed to come out of like left field, like this is some sort of funny connection. So we started looking into that, and actually here in a way, one can see that R2 and the diagonal are not really important. What matters is it's all metric properties. So what do we have so far? Right, so we have Rn, and here I have R2, but I'll just write Rn, and the diagonal, and right, and then we have, this should be 2, and then we have this space of persistence diagrams with the metric. And yeah, but then what is the generalization of this? So here we have a metric pair. We have a metric space with a closed subset, and this space is a pointed metric space. So then you can actually you don't care that this is Rn anymore. You just take a metric space and a closed subset, and you can repeat this construction and just get a pointed metric space. And so, right, so then, well, one can frame all these results in this language. One has to work a little bit. And so what is the metric pair? So here we have metric space, and this is closed and non-empty. And then you just exchange R2 for X and delta for A. And you do exactly the same thing. So now in some of the proofs for Rn, one uses the vector space structure, so one has to work a little bit more. But in the end, you can define the same space, and then one can have, and what you get, or well, one can frame this as having a functor that sends a metric pair. So you have a category of metric pairs with relative Lipschitz maps to the category of pointed metric spaces with pointed Lipschitz maps. So you have a metric pair, you apply this construction, and you get a pointed metric space. And right, so this is it. This is the functor, and then you can ask, well, okay, which properties are functorial, right? What is preserved? And then, so this is actually the first theorem. So this was a collaboration with Mauricio Chem, a PhD student who's over there. So if you have any questions, you can ask him. Luis Guijarro, who appeared earlier, and Ingrid Membrillo Solis, who she is more working with this data analysis. So yeah, so then one has these extensions. So this is complete. Completeness is preserved, separability. Then here you can show that there are optimal bijections, so sort of realizing the distance. Then if this is proper and geodesic, this is geodesic, and right, actually one understands how the geodesics look like. And then this was the upshot, is that you can generate in this way a lot of Alexander spaces in a more or less systematic way that let you then have examples where you can sort of try to see what's going on and maybe try to generalize this to maybe hopefully theorems, right? So so along the way, well, one has to catch some things up, like yeah, I mean, some of the proofs do not carry over like immediately. One has to work a little bit more. And right, so okay, but once you have this, if you forget about data analysis, you actually have this functor, right? And you have metric pairs, and you have pointed metric spaces. Then, if you remember, you have Gromov-Hausdorff distance, right? So then you can ask, well, is this functor actually continuous? So here what one needs to do is to sort of generalize a little bit pointed Gromov-Hausdorff distance to this Gromov-Hausdorff topology for metric pairs. So this is something that we did, and then with the right definition. So here this was in this paper we wrote, and then Umala Gomez and Mauricio Chele were my PhD students. So here we define the topology and prove that this functor is sequentially continuous. Then looking at the sort of what was known, and the sort of could be done, but the pointed Gromov-Hausdorff topology was not metrized. So there was so one had to sort of do some more work that they did, and with that, right? So you can prove that if you have a sequence that's a Gromov-Hausdorff conversion to a pair, then this is continuous. But here, this is only continuous for this infinity distance. This is, maybe you've heard, this is called the bottleneck distance. So this is actually sort of relevant in applications. I think it's the one people tend to compute. For the other ones, it's not continuous. But, well, so this is how it says, okay, this functor has some nicely behaved. So it also says, well, for example, if you have a discrete approximation to your space, it's going to approximate the ideal value, which is something that, well, nice. And yeah, so then to finish the talk, there's more recently, Mauricio in his thesis, so there's a connection with now optimal partial transport that was introduced by Figali and Gigli, more, I believe you can correct me, but more like inspired by PDEs maybe, right? So, which actually here, you want to do optimal transport between random measures on bounded domains in Euclidean space, but the point is that these measures might not have the same mass. So you need to compensate for that with some set. In this case, it's the boundary of the set. And then as you saw in the this distance right here, we have the diagonal where you can sort of match if you don't have things, if you don't have sufficiently many points. So actually then, well, we were onto sort of in that track, but then we saw that Duvall and Lacombe had applied, also generalized a little bit optimal partial transport for measures on bounded domains in Rn, and then sort of they applied it to also to persistence diagrams, but to this case in Rn. And then, well, and then something that we found, or at least I found slightly unsatisfactory, was that, okay, sure, these spaces, or this the space of persistence diagram with the metric, the 2 metric is non-negatively curved, but it also sort of, yeah, it's sure, but why, right? I mean, this is, yeah, so then, well, Mauricio here, he, well, frame or extended all of these to now metric pairs, and then here one has, okay, the analog of the Wasserstein space with the Wasserstein metric, and then one can see, right, that, well, this is the analog of the classic space Wasserstein result, right? That this is an Alexander space with non-negative curvature, and then one can see that this space that was coming earlier actually sort of isometrically embeds into this space. So basically, you take the metric here restricts to the metric that I showed you here, and then this gives another proof, maybe more conceptual or satisfactory, that these spaces have non-negative curvature. And then this also, well, sort of the next step is, well, try to use more optimal transport and more geometry to try to do things that potentially could be useful, right? So for data analysis, but of course also maybe for geometry, right? So yeah, so this is it. Okay, well, there are also other work so that one can prove some, well, existence of barycenters under some hypotheses. And actually, there's a related, sort of similar, around the time that we finished our paper, there was a related paper by Bubenik and Hartzog that had some sort of similar, but not the same results. So they were also onto the same ideas. So, but here I think this link with optimal transport seems promising. So now, yes, now there are also some embedding. So here this work by Bate and Garcia Pulido, this also uses optimal partial transport. So some question that people care about, or sometimes it's they call it vectorization, but it's just embedding into a Hilbert space, into a Hilbert space where you can actually do things. And then So there are some obstructions to embedding a space into a Hilbert space coming from asymptotic dimensions. So these are also some questions that people have looked at. So there are also some variants of these spaces that I mentioned. You can look at spaces that have at most endpoints and then try to see that. And so there's some work, but I think from the geometry point of view, I think there are some interesting ideas, especially if you're a metric, care about metric geometry. And then also these sort of connections makes you think about problems that are maybe not, that you don't usually think about. So yeah, so now thank you very much for your time and your questions. Thank you.